Okay, very happy to see you all connected. Do you see the slides by Fatima? Are they projected well? Oh, please confirm if you can see them or if you cannot. I'm I'm using a little bit different setup and trying to share. So Yulun is showing is fine. Good. Okay, yeah, many thanks to Fatima for agreeing to present this work. So it is coming to the final stage before submission, and we want to go through final tuning and maybe identifying if there are additional things for improvements. So I am volunteering just to serve as a slide flipper. But Fatima, if you are ready, please go ahead and present.
Okay. So today I'm going to talk about the magnetic field theory and dynamics in graphene. Next one.
Okay.
So in the top left panel, we can see the graphene lattice structure. Graphene has a triangular lattice structure with a basis of two atoms. A1, A2 are lattice vectors, and delta 1, delta 2, delta 3, they are nearest neighbor vectors. On the top right panel, we can see the first Brillouin zone. On the bottom left panel, this is the band structure we calculated using the MATLAB code. As you can see, there are six key points at the six corners of Brillouin zone, and at each key point, valence belt and conduction belt touch each other, as you can see on the zoomed in image on the bottom right panel.
Okay. Would you allow questions as we go?
Sure.
Okay. Yeah. Thank you. It's not critically needed, but it would be great to hear the main goals of the work. And for the technical part of this slide, um, is it possible? Would you think it would be? So you are writing in your panel C kx in the inverse angstroms. Is it possible to express it in just fraction of the size of the Brillouin zone, something that it goes maybe from -1 to 1? Um, I'm not requesting, I'm just checking if some sort of fractional coordinates would be appropriate. And for the panel B, what are the coordinates of the M and K points in comparison to panel C? So can one write down like for M point, Kx equals this much, Ky equals this much. For K point, Kx equals this much, Ky equals this much. I believe the reviewer may ask it and or search for this information in the captions.
Okay, so I did not understand what you said about the kx over angstrom, but I did understand what you said about the coordinates in the Brillouin zone.
Okay. Okay, I will write you the question about that you about the panel C, and I thank you for acknowledging the question about panel B. So can you tell verbally what are the values of kx and ky for m and k point?
It should be 0 and
so ky is 0
minus 22. I'm sorry, 22.
Okay. And for
x is 22 and y-x is 0.
Yes,
22.
yes. And for k point, so kx is again 22. And what is ky?
Probably 9.
Okay.
Something like this.
Okay, good. And what is the goal of the whole work? Like, what is the purpose?
So here, if light pulse or any external perturbation is applied to the graphene model, then electron what I understand here in this graphene, that since the valence and band and conduction band touch each other, there is no band gap. So if we apply light pulse, then electron will be excited, and when the magnetic field is applied, then it will influence the motion of electron.
Okay.
And our goal is to study the electron dynamics, photoexcited electron dynamics under applied magnetic field using the time evolution Gaussian wave function.
Okay. And why this dynamics is needed? Is there a challenge for industry, or is there a challenge for theory? Like, why we want other people to believe that it is interesting?
It is important in industry application. Although we are not considering the relativistic direct equation, like relativistic mechanics, but this electron, the probability density of electron moves like cyclotron motion, and if magnetic field applies, then Landau level creates, and they can carry information, quantum information. But in our case, we are not considering those relativistic cases. We are considering non-relativistic Schrodinger equation.
Okay. So interference can live for a long time. At least there is a hope.
Yes.
Okay, good. Let me know when you want to go to the next slide.
Yeah, next slide, please. So as you know, the graphene has a honeycomb lattice structure. This structure can be described by tight binding Hamiltonian. And if there is no external potential or magnetic field, then one can get the energy band structure from this tight binding Hamiltonian. As you can see, the equation EK equals plus minus something, and here plus for valence band and minus for conduction band.
Okay. And would you please tell what are the definitions of A, B, C, C, dagger?
A, B, there are lattice at the sides.
Okay.
And C, A, C, A transpose, they indicates the annihilates and the creates of electron. epsilon A is the hopping energy, first nearest neighbor hopping energy, and TA is next nearest neighbor hopping energy.
Okay. Is it possible to, would it be reasonable to flip back to one slide to explain what is A and what is B?
Yes.
Okay. So is it right that each yellow side is A and each brown side is B?
Yes.
Okay. And the T lowercase is the probability of jump from one side to another one. Here, hop.
What was that?
T sub AB is hopping.
Mm-hmm.
Okay.
Yes, it's for next nearest neighbor. From yellow to yellow.
Mm-hmm.
Wait.
Wait.
And for yellow to brown.
But here it is AB, so it is from yellow to brown, and I do not see yellow to yellow. Yellow to yellow will be T sub AA.
There is epsilon A.
Huh?
In the first term, there is an epsilon A that is for nearest neighbor.
No, it looks like it is the energy on side energy. It is energy of electrons that sits on side A without hopping. So it's diagonal part of Hamiltonian.
Oh, okay, so then, okay, I see. Mm-hmm. This is on-site energy, yes, epsilon A. And the next nearest neighbor hopping energy, I just ignore.
Okay. Okay. And how does one obtain these energies out of the Hamiltonian?
After solving the Schrodinger equation.
So just by diagonalizing this Hamiltonian matrix, right?
Mm-hmm.
Okay. Let me know when you are willing
yes,
to.
Next
okay.
Case.
I don't know if I put it a little, expanded it so maybe it is better visible. So what?
So this is the part of MATLAB code used for calculating band structure in the panel C on the second slide.
Okay. Uh-huh. So plus is for electrons and minus is for holes, right?
Plus is for electrons, plus is for holes.
Please correct me if I'm wrong.
I guess plus is for holes and minus is for electron.
But electrons have positive energy and holes go negative.
Negative. Yes, negative for holes and positive for.
Okay, so this one is for
electron, yes.
Electron, and this one is for holes.
Mm-hmm.
Oh, holes. H plus. Okay. So E plus is LUMO, and E minus is should be then HOMO. Okay. Let me know when you want to go to the next.
Yes, like this. So since we are considering time evolution of Gaussian WAVEPACKET, here first two lines for wave function in position space, and if we calculate first Fourier transform of wave function in position space, we will get wave function in momentum space. That is shown in the 3 lines. There's a FFT phi naught x, like these 3 lines.
Mm-hmm.
And the next slide is.
So a brief comment, and Yvonne, Aaron, and David, please interrupt anytime. I'm just so excited, and I do not have, and I may forget to ask if you have questions, but feel free to interrupt and ask questions as we go. So this slide could be better if you need to present this once again after diagonalizing, after explaining diagonalization of the magnetic field Hamiltonian. Because first one solves the time independent Schrodinger equation and then time dependent. So this slide, initial wave packet, relates to time dependent Schrodinger equation. So it a little too early. Everything seems correct here, but it seems a little too early in the logic to present it, because we do not know, it's misorder. Make sense? Okay, so next slide.
So since we are considering 2-dimensional momentum space, so we consider k point along 2 directions and 2 indices for 2 dimensions. And then the maximum number of k point, 55. Here we introduced a super index which consists of 2 indices, I and j, and we calculated wave vector as a matrix. And then the next MATLAB loop, we converted wave function matrix to a vector wave function. Since it is convenient to display wave function as a vector.
Okay. Okay, I see. But right now it does. It is related to initial value of the wave packet for time propagation, right?
Mm-hmm.
Okay. Let me know when, if you want to go further.
Yes, next slide, please.
Okay.
When a magnetic field is applied to a graphene model, then after applying magnetic field, you consider the z direction of angular momentum. And if this slide shows how the z direction of angular momentum is derived here.
Okay. So you're telling that for magnetic field orthogonal to the plane of graphene,
Yes.
The only z component of angular momentum participates in the interaction.
Yes.
And one needs only z component of angular momentum. So this part will be used in the Hamiltonian, right?
Mm-hmm.
Okay. And can you tell verbally what will be the next slide before we go there?
Next slide is like how we introduced this z direction of angular momentum and Schrodinger equation using MATLAB.
Okay, so it will be practical implementation of this operator which acts on different degrees of freedom on x and y, right?
Mm-hmm.
Okay.
So this is the main equation here. As we can see, it's not highlighted, but not the arrow. It indicates by arrow. And we can see the equation for z direction of angular momentum as well. Mm-hmm. And another thing is here, we converted 4 indices tensor to 2 indices matrix.
I do have a question. It's a little provocative. I know the answer, but I want to learn from you how you would explain it. So can you please tell why there are these delta functions? So what is the meaning of this unity operator in this line?
When magnetic field is 0, then the electron will be localized at k point, so it integrates by the delta function.
Maybe I'm wrong, but I think it should be different explanation. Can you try once again?
I don't know. Is it part of Hamiltonian? So one is kinetic energy and the other one is potential.
No. Let's think together. If David, Aaron, or Yulun have an idea what is written here and why this unity operator is needed here, just any discussion, any suggestion.
It is a diagonal matrix, right?
Yes, yes.
So it makes the Hamiltonian also diagonal. That's all.
Well, the Hamiltonian in this variable, does have 4 indices. I1, I2, J1, and J2. So instead of square matrix, it is tensor with four indices, right?
Yes.
And then we do know that indices I1 and J1 refer to x dimension, and indices I2, J2 refer to y dimension. So, and we do know the partial Hamiltonian that acts only on x degrees of freedom. And we know the Hamiltonian that acts only on y degree of freedom. But overall Hamiltonian should act on both x and y. So the Hamiltonian is composed of product of these two objects which have non-coinciding indices. So when we perform activity in respect to x degrees of freedom, the y degrees of freedom are staying unchanged. When we perform activity in respect to y degree of freedom, the x degrees of freedom stay unchanged. So this is needed to implement operators for 2 degrees of freedom. And if maybe there will be a problem project that Yulun will do in the future for either making chemical reactions with 2 reaction coordinates, or 1 reaction coordinate can be nuclear degree of freedom and another can be photon. Then we will need to implement the same idea. So when one operator, when we want to build the overall Hamiltonian, when it will be composed of parts. So one partial thing affects only degree of freedom 1, and then it needs to multiply it by this unity operator in respect to second degree of freedom, and then opposite. When we affect second degree of freedom, the first one should be represented by unity operator, because overall number of dimensions should be kept. Like if there are 2 independent variables, the operator should have 4 indices. Make sense?
Mm-hmm.
Okay, and you did put another arrow for the angular momentum. Would you please give comment about this implementation of angular momentum?
So as we can see in the equation, it's the first on the right hand side, first term is looks like first term is px. It should be the other way around.
Okay.
So in the equation, it shows that first px, then x.
Okay, so
minus x p y.
So it should be d.
First term is px y minus
d,
x
dx
dy
times y, right? And then second part should be x times d dy, right?
Yes.
And since x and y degrees of freedom are counted by different independent variables, the arguments for this px and y are non-coinciding. So it's I1 J1 and I2 J2 for x and y components. Okay. And I do believe that in addition, this operator, angular, is given angular momentum in Cartesian coordinates, right? In space.
Mm-hmm. Yes.
And if you present the few lines of code below, there should be similar operator for angular momentum in momentum space. So it's something like angular p, right? Okay. Please let me know when you want to go to. Okay. Thank you.
And in this slide, it shows how we coded time evolution operator in MATLAB.
Very good. So there are three lines that look very similar to each other. Do you remember which one of them is used later? Which one is correct? So with imaginary unit, with minus, or with plus?
I think middle one is good.
So middle one, okay.
Middle equation.
Maybe I would check maybe the first one, but we can double check later. And this segment in here should be the full Hamiltonian for the system in magnetic field. Should be like H equals H naught, which is tight binding minus magnetic field times LZ. And then this Hamiltonian is plugged into the evolution operator. Okay.
And the next slide, please.
Mm-hmm.
This slide shows how we inserted time evolution operator into the wave function.
Mm-hmm. Okay. So I do have question. Should be there Bohr magneton in front of this interaction term, or we in the units that we select it can be skipped?
It was selected as one.
Okay, but if we would write equations in general, one may put this proportionality constant. Okay. So what's the name for this procedure?
Which procedure?
Solution of time-dependent Schrödinger equation by evolution operator? Would it be correct? Or there is a better name for this?
I'm not sure.
Okay. So you do not mind call it evolution operator for time-dependent Schrödinger equation? Okay. So up to okay. I think there is one slide missing. Let me edit.
Yes.
Let's edit together right now. Just make it as so tight binding Hamiltonian minus LZ magnetic field, and then one is applying this full Hamiltonian to the unknown wave function, and this will be an equation to find for wave function in the momentum space. right? So time independent Schrödinger equation. And all slides up to here were methods, and in the next slides you are going to present results, right? Okay, let me know when you want to go to next.
Yes, please. Now, here we can see the eigenstates. We calculated 500 eigenstates. Here we can see for each value of magnetic field only 3 representative eigenstates and their corresponding energies. And these eigenstates are shown in first Brillouin zone of reciprocal space.
Okay.
For lower value of magnetic field, looks like the electron probability density distribution is localized around the key point, and if the magnetic field is higher, then the electron probability distribution delocalizes around the key points.
Okay. Other questions from David, Aaron, and Yvonne? Any suspicion? Any just something seems missing? If I would, yes, please, please.
How do these figures relate to the dispersion cones that are shown in this example for figure 1? Like, how do these states relate to those? Because so I would think if you could find the states.
And actually here this electron probability density distribution we consider only in conduction band. So we did not consider valence band, so it's just the conduction band. So and each corner is one cone in the Brillouin zone.
Aaron, are you satisfied, or you want more? Let me bring the dispersion curve and copy paste it into here, so you can look at them together for better analysis. But it is the very relevant and great question.
I think I realize now my question doesn't make sense. Because the dispersion, I think the dispersion curve is just energy. Right, it doesn't relate to probability densities in the Brillouin zone.
So what I understand your question is how this electron probability density related to the cone in the Brillouin zone, right?
Right.
For these electron states, we consider only the conduction band. If you look at this band structure, we consider only the conduction band.
So then in conduction band, like where would you just consider the lowest point of the cone? Like how would those states be distributed?
Yes. So if the state number is 1, that would be the lowest one. But here, if you look at the top row, the first one is state 171. So it should be somewhere like higher than, so it's not exactly at the lowest point of the cone, higher than the lowest point. You know what I mean? Since we consider like So if the conduction band is divided by many states, right? So we consider 171, 251, and 351.
Right. So I guess my question would be, as a reference, like what would be the distribution without the magnetic field? Like, does it change the distribution very much?
You mean, does the distribution depend on the magnetic field?
Right, so I guess...
Yeah, it depends. Like the electron distribution depends on the magnetic field. If the magnetic field is higher, then the electron probability distribution will be delocalizes.
So in the limit of no perturbation, I guess your states would be more localized.
Without perturbation, yeah, more localized. If there is the higher the perturbation, the electron probability distribution will be delocalized, more delocalized.
So without magnetic field, the momentum is conserved, and eigenstates will look like two-dimensional delta functions. So on this colorful diagram that Fatima is showing, the eigenstate without magnetic field will be only one dot, 1 point. And as magnetic field increases, the eigenstate is distributed over several dots. And I hope to hear from Fatima the following keywords at the end, at the time of conclusions, that magnetic field violates conservation of momentum. Because without magnetic field, the momentum is conserved. If we set up electron in the plane wave state with certain momentum, it will be certain for eternity, forever. But if there is a magnetic field, then momentum is changing. So it's one aspect. Another aspect of the question by Aaron, which is very relevant. This potential curve, the conduction band that we are focusing at, can be approximately considered as potential energy surface. It is not potential energy surface, it's dispersion. It depends on momentum. It is more kinetic energy rather than potential. But in some sense, it is energy profile. And you can find eigenstates in this analog of potentials. So it will be some peaks which will be maxima above the minima of the potential, right? And if there is external perturbation, the shape of these eigenstates will be perturbed. But there is a challenge for human brains. As soon as we apply magnetic field, we cannot plot the Hamiltonian in the as this potential dispersion curve, because the Hamiltonian is 4-dimensional, and this line would become discontinuous. It will be something that humans' brain cannot imagine. So it's more reasonable to speak only about eigenstates, which we still can imagine because they're 2-dimensional. Another thing, before we switch on magnetic field, there is a 1-to-1 correlation between value of momentum and value of overall energy. So we can draw this shape. As soon as we launch magnetic field, momentum stops being a good quantum number, and energy cannot be drawn, can be defined as function of momentum. We can only list eigenstates, and eigenstates themselves will be distributions as function of different values of momentum. So I understand the concern that you try to express. The things that Fatima is presenting and we are considering is away from ability of human to imagine everything in a mechanical way. So we can compute it with equations and codes, but by human brain we cannot imagine the objects that we are describing. Does it address your question in part?
Mm-hmm. Yeah, I have a little bit better idea about if you look at these figures.
Okay, okay. And I foresee that reviewer of this of the paper when it is submitted will ask questions like this. There, even if all results are absolutely correct and interesting and relevant, there is a challenge for human to understand it, and it will be discussion between reviewers and authors for sure on this aspect. So question of error is very relevant, and it at least prepares authors to address questions of reviewers in the future.
Okay, next slide.
Okay.
On the top panel, we can see the density of states at different magnetic field values. First, density of states for without magnetic field. We can see if the magnetic value of magnetic field is increasing, the density of states are decreasing. The blue line and yellow line represent conduction band and valence band respectively. On the bottom panel, we can see the first 50 eigenstates and their corresponding energies. Although we have calculated 500 eigenstates and their corresponding energies, as you can see, when magnetic field, the value of magnetic field is increasing, and the energy of lowest eigenstate is decreasing, and it will be continued for higher magnetic field.
Okay. Fatima, would you think it is possible and relevant to show the density of states in a narrower range? Because this going of the density of states down after energy more than 0.5 is when we go away from Dirac-Cohen region, and it will need more discussion. It could be an artifact of calculations, or even if it is a true thing, it may need explanation. So I think it will be easier to present if you focus only on the energy range close to Dirac-Cohen, in vicinity of 0. So it would be really great. There is another thing that I do not know how to interpret, and like two things, and reviewer may come after us. So first thing, there are 6 Dirac cones in the Brillouin zone, and in the 0 magnetic field, energies of these 6 cones should be equivalent, degenerate. So one would expect to have 6 degenerate points at lowest energy, but by some reason we have 4 rather than 6. If I will be reviewer rather than co-author, I would complain and ask why this is happening. So if anyone has an idea, please express. So we need to figure it out and address before submission. Like here with magnetic field, it looks like almost degenerate, and then the next batch looks closer. So this one it looks better. For description of this graphene, when Fatima is presenting the model, it uses this A and B vectors, which are, or A1 and A2, I think A1 and A2, which are not orthogonal. A1 is not orthogonal to A2. And maybe in order to model the things, instead of X and Y, one needs to use different set of coordinates, like A1 and A2 as coordinates which are not orthogonal, and then it will be more reasonable. Or maybe one needs to redo everything in polar coordinates, like distance from gamma point and then the angle. It doesn't seem possible to do it in a short time, but at least some ideas to understand and address this inconsistency would be great.
So you mean that I need to do this before submission?
Only verbal explanation. I do not believe that we can redo the codes. If we try to redo the codes, it will take at least 2-3 months to debug and make it working. But we can verbally address that we do see weaknesses, and we know where they originate from, and we know how to fix them in the future.
So it can go to discussion then.
Yes, exactly. So another thing, in panel D and E, the energy of the orbital in the conduction band is bigger than 0. And in panel F, there are several energies with energy which we attribute to conduction band is smaller than 0. So this is also, I wouldn't say wrong and suspicious, but it is something very novel and mind-throwing. So we need to be ready to explain to reviewer how to interpret it. Of course, we can remove this result and not show it, but a smart reviewer will ask about it. So it's better if we develop an explanation. So having few states from conduction band dropping down the 0, the Fermi energy, would probably correspond to several states from valence band to penetrating into conduction. So it is mutual penetration of valence and conduction band. And it seems like conductivity, magnetic effect for conductivity. So if this is true, this would mean that increase of magnetic field would increase the conductivity. So let's plan on thinking and discussing this in at least between us and at most in the discussion section. So it seems like mutual penetration of conduction band and valence band. So this negative values of energies. May I ask if there are questions or comments on these aspects from David, Yulun, or Aaron? do you see major problems or major suspicion, or it seems like a technical issue that is okay to explain verbally and as a natural effect rather than artifact of computation? So I would probably check keywords in literature for magnetoresistance and magnetoconductance. So if increase of magnetic field can change the conductivity. And this is not the main aspect of the paper, but it if everything is correct here, it can be a big breakthrough and will attract citations. So it will be something substantially novel. And so we shouldn't fear, but just try to interpret. Whew, okay. Let me know if when you are ready for the. I don't have more questions. Okay. Yeah. Thank you. Should I run the video?
Yeah, and this is the movie of 500 eigenstates at 0.7 Tesla.
I think when we do video, when we transfer video between computers, it may skip some snapshots. So it should be continuous snapshots. Can you explain what to see and how to interpret it?
So electron distributions are changing with the corresponding number of eigenstates, right?
So since 500 eigenstates is too large, it is quite a challenge to show all of them as panels in figures. And instead, Fatima is showing scanning through all eigenstates as a movie. And one can see that some of them are localized near the red dots, and some of them form shapes in this momentum space.
It's kind of confusing because with increase of time, you are also changing the eigenstates.
Sorry, I apologize. There is no time here.
Okay, so this is just a final distribution of eigenstates.
It's just a scan. So we do have. Let me do a little drawing. So we do have phi sub I of kx ky, and to avoid the imaginary part, we do square, and then we run for the index from 1 to 500 and just show them, but there is no time. They all are static. Okay. Fatima, do you have more comments, or you want to go to the next one?
The next one.
Okay.
And this is the same thing, 500 eigenstates at magnetic field 1.93 Tesla. Here we can see that electron distribution area is more localized.
More delocalized. Okay. Can you make a comment about this delocalization of the eigenstates and the cyclotron trajectories?
I'm not sure.
Um,
So in the next
no.
slides,
Before we go to the next, if the can you tell what are cyclotron trajectories? And we here are chemists. You have a physics background, so just teach us what are cyclotron trajectories.
so if magnetic field is applied to a free electron,
Uh-huh.
then electron moves in a circular motion according to the Lorentz law.
Okay. So which means that eigenstate, if you convert this classical trajectory into the eigenstate, then it will be like a ring in this axis. So in kx, ky, if it corresponds to cyclotron motion, it will be some probability on the surface of a circle and zero inside and outside, right?
Mhm.
So it is how we should interpret this eigenstates, and some of them show this circle like shapes, maybe not exactly, but something circular, and it is very expected and very positive results. So this should prove that we do something in the right way, and this should satisfy the reviewer. So it's a good point. Okay. And any other?
Next slide.
Can you, before we go to the next slide, can you please tell what should we expect in the next slide?
The next slide is electron probability density distribution under applied magnetic field.
I can pretend that I do not understand you. On this slide that we are watching right now, it is also electron density distribution under applied magnetic field. What will be new in
This is static. And the next slide will be dynamics.
Okay, so until now, we were solving time-independent Schrödinger equation. And starting from the next slide, we will look for a solution of time-dependent Schrödinger equation, right? Okay.
Here we can see the snapshots at a different instant of times. Snapshots of electron dynamics of electron probability at density.
Mm-hmm.
And we can see if we apply more of a higher value of magnetic field, this electron probability density distribution is more delocalized.
Mm-hmm. So,
and
yes,
we are just for simplicity, we consider only one direct point, but it's supposed to be happen from all of these 6 direct points. If we consider the motion from all of these all 6 key points, then they should form a cyclotron-like trajectory.
Okay. Is it possible to say that when we have smaller field and longer time, the shape is approximately the same as if we have larger field and shorter time? Is there similarity between these different time points in different time steps?
Yes. Mm-hmm.
So approximately, increase of field or looking for a longer trajectory will give the same results. So with larger field, it just moves quicker. Okay. I do have another question. Based on the discussion in the previous slide, I would expect that this initial distribution will just move on a circular trajectory here and there, but instead it splits on several pieces and it forms interference fringes. Can you please share your vision why it creates these interference fringes?
I'm not sure.
Just try if it's inside the group. So if it is not quite adequate, it's fine.
As I understand, then if electron, if it's like a kind of interference, constructive interference.
Yes. But why electron cannot go completely on a circular orbit? Why it splits on several peaks? And everyone is invited to contribute ideas.
My first thought would be spin, but it doesn't seem like you account for spin variables for your density. Is that correct?
There is no spin here.
There is no spin. So just a second. So let's just utilize this analogy with eigenstates in the potential. So if we start from Gaussian wave packet above the minimum and then assign it to move in a certain direction, in the free space, it will go wherever we send it. But here, when it is inside this minimum, it hits the wall of the Dirac cone and reflects back. So we do create bound states. So it's eigenstates in the vicinity of the Dirac cone, and bound states like S, P, D in hydrogen atom, or in the square box, it is n equals 1 and n equals 2 states with different number of fringes. So it looks like signatures of formation of eigenstates in the vicinity of the Dirac cone. So one may try to interpret formation of these fringes in terms of eigenstates that we discussed on previous slides. So if the value of magnetic field is not sufficient to jump over the potential barrier, so here there is a barrier, and if the magnetic field is not strong enough, then instead of overcoming the barrier, it will bounce forth and back, and it can be composed. It can be expressed as a superposition of eigenstates which are localized in vicinity of this Dirac cone. I can be wrong, it's only hypothesis, but I invite you to criticize or discuss if it sounds possible explanation.
If this is the case, can you just track some of the eigenstates instead of the WAVEPACKET? Like the high energy one?
What do you mean track? Just look at them or start dynamics from eigenstate?
I guess you can do it possibly.
Huh?
I guess either of them works. So I guess my point is for eigenstates with high energy, you can just overcome the barrier, right?
Yes. So we can either well, I'm not telling that we need to do any calculations right now. It's more time for analysis. But if you hypothetically do more calculations of the dynamics with higher value of magnetic field, then WAVEPACKET will penetrate into different Dirac cones. It will overcome this barrier on one hand. Or on another hand, if we start from the eigenstate with large energy rather than Gaussian WAVEPACKET, it will be automatically spread over the whole brilliant zone, and it will be long-lived circular-like state. So if there are no more critical suggestions, let's, Fatima, when you're ready, let us know if you want to go to different slide.
Yes, next slide. So this is the movie of dynamics of electron probability distribution at 0.7 Tesla.
Oh, it doesn't. Ah, this one doesn't play. Okay, I do not want us to lose the opportunity to watch it, so I will. I'll bring it from YouTube. I think we should have it on YouTube. Just in a So I believe this movie created by Fatima scans over very for like 25 femtoseconds, and the step is a small fraction of femtoseconds. So as movie goes, we go quite slow. Okay. Okay. I'm watching and enjoying it, but okay. Let me. Okay, sorry. Let me do it. Please say yes.
Yes.
I do not see you right now. Okay. So now we are coming closer to the end of the project, and I did set a loop for it's and also it looks like first it squeezes instead of becoming more broad, which is also uh, a little interesting. And then after some times it starts becoming broader and splitting on several fringes, on several peaks. Any comments about this movie?
No.
Okay, okay, let's watch another. So this was the lower value of magnetic field. Let's.
I think this one is for higher one.
No, it tells 0.7 Tesla. Maybe I misinterpreted and uploaded different one. And here is the one for bigger value. So if I'm wrong, it will show less dynamics and so in my labels it is 1.93 Tesla. And now we are about third of a trajectory, and it looks like a half of the trajectory with smaller field.
So I think you uploaded the same one.
Okay, and this seems. You think I did upload it the same one under different names?
Yes.
Okay. You may try to upload the right ones and share the links, but after the meeting.
But I don't know how to do it this way.
Oh, okay.